Hello. Having discussed about the scattering in a central force field, we shall now be moving over to the application part of it where we will be discussing the Rutherford scattering cross section and the formulas that are associated with it. To start with, we consider the case where we have a nucleus to which an incoming particle, positively charged, is approaching, and supposedly it's approaching along this line. So this is the line of approach of the particle, of the positively charged particle, towards the alpha particle, or towards the nucleus, beg your pardon. So yes, obviously in Rutherford's experiment we have the alpha particle approaching the nucleus. Let's for example take it as just a positively charged particle. Now this particle present at this point, let this point be P, as it approaches the nucleus, it tends to get diverted along a certain line which is a curved path. It obviously cannot reach the nucleus because the nucleus will provide it with a repulsive force field. And this is the axial line or the axis from the nucleus that we are considering at the moment. And what happens is that this particle, as it is approaching, it cannot go in that straight line, and in fact it takes a hyperbolic path, just like this, symmetric about that horizontal line that I've just drawn, that is ND. We take that line as ND and it is symmetric, the hyperbolic path is symmetric about that line ND. We'll be discussing why all of that is happening. Now if I just extend this point, suppose the particle was somewhere over here, it had started from that point A, we are considering its journey, and at the point P is the point where it starts to divert from its path and get scattered along DB. So this is the incoming path is along AP towards D. It was actually heading from AP towards N, but now it has got diverted, it has got scattered along DB. The line of incidence as well as that of the scattering is considered asymptotic for easier approach towards the problem. So the asymptotic line that we have to consider, in order that we obtain an asymptotic line, what we do is we construct a hyperbola near the nucleus as well. So this is more or less the case, but first of all I'll be doing the other way around. What I'll be doing is I'll be constructing the asymptotes first, and then I'll be considering the hyperbola near the nucleus, because it's actually the assumption that we are making for getting the asymptotes right. So here I have the point where along which I am considering the asymptote. An asymptote is obviously something which won't be touching those lines, the lines of the hyperbola or the curve hyperbola. Then it is something like this. It's a straight line and it extends along this path as well. So this is one of those hyperbolas, one of these asymptotes associated with the hyperbolic path, and that is for the incident case. And as for the scattered case, we have another asymptote which extends along this direction, and if we take it to the other side for symmetry, we end up like this. So this is the asymptotic line which is associated with the hyperbolic path, and conversely we'll have a hyperbolic, we can construct a hyperbolic path here as well, but that won't be really of much use. But for simplicity, in case of hyperbola, we are considering the asymptotes as well as the hyperbola, in this case the complete hyperbola. So here the angles concerned, let us take this angle as phi and this angle is alpha, and because we have the hyperbola to be symmetric about that nd axis that we have constructed going through the nucleus, so that those two angles will be alpha at the top and at the bottom as well. Let's take this angle that the incident particle was making with the nucleus initially to be theta. So this is theta. And as we know from our study in the previous case, the perpendicular line that the perpendicular dropped from the nucleus towards the path or towards the line of approach of the incident particle, that is termed as the impact parameter, and we had given that as B. So impact parameter B, let me write it in some other place for better understanding. Okay, so I hope this more or less helps, the marking of B, that is the impact parameter. So the positively charged particle approaches with an initial velocity, supposedly let it be v naught, we take it as v naught, and the scattering in a repulsive force field has been shown over here in the diagram. So there we have it. Now the repulsive force that will be acting that will be equal to we take the charge of the nucleus to be capital Z times of E, while the charge in case of the approaching particle to be small z times of E being the unit of charge in this case. Now we could have taken Z1, Z2, but I don't know why I'm taking it like this, so let's take it for the time being. So we have 4 pi epsilon naught times of inverse of the square of r, where r is, as I've forgotten over here, r is the distance that we are taking at that point of time. So this increases rapidly as the particle approaches the nucleus. Now the path changes from the straight line to parabola, and we have AO. So as you can see over there, that point that I have marked, that is A, not there. AO is the direction of the incident particle, and we have BO to be the direction of the scattered particle. It's the same particle, of course, but at one point it is incident and at the next moment it gets scattered, so scattered particle. And as for the motion of the charged particle in the central force field, we have the equation of the path. So the equation of the path in case of the motion of a charged particle in the central force field, which is varying obviously inverse of r squared, varying as inverse of r squared, is given by L over R, which is equal to 1 plus E times of cos theta. We had discussed this earlier in our in our segment with scattering, involving scattering, where L obviously we have to be equal to J squared over mk, where k is the constant. In this case, k is equal to all that is there in case of just leave the r square out, and all that remains in that repulsive force is what we have as k. And so k over here is the ze, the capital one, and the small ze, both of them, divided by 4 pi epsilon naught. So that is what we have for the value of k. You might consider it as negative as well, because in the real formula for force we had that to be negative. So here we can take it as negative, because negative of negative is giving a positive value over here. The eccentricity, as we know it, is equal to 1 plus 2 ej squared divided by mk squared, the k, that same k that we have taken on the left. So these are some of the values that are concerned, and thus we have, having all of these values, of course, we can substitute the value of k in those equations, and also the value of yes, essentially that will be k in all of those equations. So now the total energy as we know it, initially, at least initially, the total energy that's going to be E, which is equal to half m naught, sorry, not m naught, m times of v naught squared, m being the mass of the incident particle. So we have mv naught to be equal to 2 times of me. Now where does this come from? Obviously we know that momentum is equal to square of the momentum divided by 2 times the mass is equal to energy. So that is why p square is equal to 2m. P square by 2m is equal to E. So the 2m gets cross multiplied and we have p square as 2me. So p, which is equal to mv naught, is equal to the root over of 2me. So that's where we get this. Now mv naught times of p, not p but b in this. Now take a look near the nucleus over here. What we get is that mv naught being the approaching distance, and as we know the distance from the nucleus, the perpendicular distance, that is b, so that is mv naught times of the distance, and that is equal to the angular momentum, if you remember. Or we have mv naught to be equal to j over p, not p, b, which finally equates to 2me under root. Or we can have j to be equal to b times of the root over of 2me. Now all of that in place, so now we substitute all those values, that is in case of j, the value of j over here, the value of k over here, all of that is now going to be used in the value of E that we have, that is for eccentricity. And let's check for the case where we are getting the hyperbolic path. Now, in case you don't remember those values, you can write them down. I will be writing them in the next page, so it will be helpful for you. So we have E to be equal to all under the root 1 plus 2ej squared, and in the denominator we have mk squared over there. Now we are going to use all those values that we have just studied. So we have all under the root 1 plus 2. The e stays there, of course. For j squared, we have just learned that that will be equal to b times of the root over of 2me, and that can be squared. And as far as k is concerned, we have the value of k, the m stays as it is. The value of k is ze times of ze, if you remember, and all of that squared individually because we have k squared in that case. And at the top we have 4 pi epsilon naught squared. Now k was negative, so k squared is obviously going to be positive in this case. So with all those values there, what we get is e to be equal to, finally, 1 plus 2e times of b 4 pi epsilon naught divided by z times of z times of e squared, and this entire thing will be squared because you can see the masses cancel out, and well, we could have multiplied the 2 with 4 to get 8 over there, but never mind. This factor that we see, that is obviously positive, the bracketed term squared, that is positive, and that added to 1, the value under root is going to be greater than 1, and so we have the value of the eccentricity to be greater than 1, and thus we have that representing a hyperbola. So that just states that the path that the particle is going to take while approaching the positively charged, and in this case the repulsive force field, is going to result in a hyperbolic path. Now the hyperbolic path must be symmetric, as I mentioned about the direction of the periapsis. The periapsis is the closest point that the particle takes. If we observe that point, the D that we had obtained or we had marked over there in the figure that you see, the point D is the periapsis, and that must be symmetric about that point or that path or that line along which it passes. Now that scattering angle over there is obviously phi that we have marked. So the scattering angle phi here is going to be equal to the total angle that we see is 2 pi. So the total angle C that we have is not 2 pi, but the straight line that we are taking A, O, and towards the nucleus, we haven't marked that, so let it be like that. So that total angle is phi, and that, if you see, is pi minus 2 times of alpha. So pi minus 2 times of alpha, or we are getting the value of alpha to be equal to pi by 2 minus phi over 2. And the alpha is obviously angle between the direction of the incoming asymptote and the periapsis direction, if you would like to have a look at it, that we had considered. So we have the value of alpha to be the angle between the direction of the incoming asymptote and the periapsis direction. Now the asymptotic direction is that for which we are getting the value of r, if taken to infinity, then we'll have theta to be approaching alpha. As you can quite clearly see from the figure, if r is going over to infinity, we have theta to be approaching alpha over there. As a result of that, what we find is the equation for the path now changes. It is 1 plus e times of, it was cos theta. Now theta has approached alpha, and the term L over R, as R tends to infinity, goes to 0. And so we have the value of cos alpha to be equal to the negative of 1 over e. And as we know, alpha that we have obtained over here to be equal to pi by 2 minus phi over 2. So we can take that value cos pi over 2 minus phi over 2, and that is equal to minus of 1 over e. And so we have the value, this is nothing but sine phi over 2, that is equal to minus 1 over e. So e squared is nothing but cosec squared phi over 2, or cosec squared phi over 2, as we know, is 1 plus cot square phi over 2. And this is e squared, and if you take the square of e, because e we have obtained over here, this is the value of e that we have obtained, and squaring both sides we get 1 plus that term. Now, so comparing this with this, the entire thing can be compared obviously. So the ones get cancelled because the square will result in the root over getting out of the equation. So we have cot square phi over 2, or cot phi over 2, because the square terms are also going to get reduced. So cot phi over 2, cotangent that is, cot phi over 2 is equal to the bracketed term there, that is 2eb, we can take it as 8 now, 8eb 4 pi epsilon naught divided by the small z followed by the capital Z times of e squared. So this is one way to find the scattering angle phi. So we have a solution or a formula to obtain that scattering angle phi. Now, with respect to the impact parameter, what we get is, from this above equation we have the value of b to be equal to the reciprocal of that multiplied to cot phi by 2. So this is z times of e squared at the top, multiplied to cot or cotangent of phi over 2 divided by this entire thing. Now this entire thing, that is 8 times of e, the 4 is not there, 8 times of e times of pi epsilon naught. Let me just get rid of that 4. So this is more or less the value of the impact parameter. Now let me just box that. Now, because we know the case of the scattering cross-section formula, that we have dB, we wish to obtain the scattering formula that depends on the value of phi, and for that, for obtaining sigma phi, which is obviously equal to, as we have learnt right from the previous video that we considered, that is a negative of b over sine phi followed by dB over d phi. So what we do is that we use this value of b that we have obtained, we also take its derivative with respect to phi, and then we put that in this equation for the cross section, and thereby obtain the Rutherford's scattering cross section formula. So I leave that to you to do the simple derivative as well as the value of b over there. What I can give you as a hint is that the denominator term sine phi, that can be taken as 2 times of sine phi over, that is sine 2 phi over 2. So that gets to 2 times of sine phi over 2 cosine phi over 2. This that we have over here is nothing but 2 times of sine phi over 2 cosine phi over 2, and you use this, and the rest of the cases where we put the value of p and the derivative with respect to phi, we put that all in place, and the final expression that we are going to get over here is going to be of the form as follows, that is phi sigma or over phi, or sigma as a function of phi, to be equal to 1 over 4 times of, we follow it up with a bracket, so that is multiplied to z times of z e squared divided by 4 pi epsilon naught times of, well, again we can take it as 8 instead of 4. 8 pi epsilon naught multiplied to e, and that's again squared, and finally the cosecant of phi over 2 to the power 4. So this is the famous Rutherford's scattering cross-section formula, and the scattering cross-section, or the number of particles scattered per second along the direction phi, are therefore proportional to the cosecant phi over 2 to the power 4. They are also proportional to the square of the charge, that is z times of e, and square of the charge of the particle, that is small z times of e, and that is also inversely proportional to the initial kinetic energy, the square of the initial kinetic energy, that is E. So here are some of the things that we can consider, and all of those things being constant, we can just take if n phi is the number of particles scattered along the angle phi, right? I am writing the formula over here. So we have n phi as the number of particles which are scattered along the cross section phi, making the angle phi, per second. Then what we can do is we can represent n phi as the constant term multiplied to the cosecant phi over 2 raised to the power 4. So that is the expression for the scattering of particles, and this is the Rutherford scattering formula that we have deduced. I hope it was easy, but in case you have any doubts, you can always practice and ask your queries. So that's all for this video. We'll be continuing with more in case of classical mechanics. Probably we'll squeeze in a video related to the numericals which are associated with the topic. That's more or less the end of the two-body central force problem. We'll be moving over to the next topic, which I shall discuss in the next video itself. Till then, thank you for watching.